All right, if you've ever had to deal with a messy database, you know the feeling. Data that's inconsistent, unreliable, it's a total nightmare. Well, today, we're going to tackle the process that brings sanity to that chaos: database normalization. Let's dive in.
So here's our game plan. First, we're going to pinpoint the actual problem, data redundancy, and all the chaos it brings. Then we'll grab our toolkit, the key concepts we need to fix it. After that, we'll start climbing the normal forms, which is just a step-by-step way to clean everything up. We'll double-check our work to make sure we didn't break anything. And finally, we'll talk about why this whole process is so critical for any solid database design.
So what is the big deal with messy data anyway? Well, the core issue, the big one, is redundancy. See, when you store the same piece of info in more than one place, you're not just wasting a little bit of disk space. You're basically setting a trap for your future self. These traps are called anomalies, and trust me, they can completely corrupt your entire database.
Take a look at this table. It seems harmless enough, right? But look a little closer. Student 101, John Doe, is taking 2 courses, so his name is listed twice. And Professor Smith is teaching 2 different courses, so her name is also repeated. This repetition, this redundancy, it might look small, but it's the root cause of 3 huge types of data corruption.
First up, we have the update anomaly. So let's say Professor Smith gets married and changes her name. To fix this in the database, you have to find and change every single row where her name shows up. If you miss just one, bam, your database is now inconsistent. It has 2 different names for the same person. Your data's integrity is shot.
Next, the insertion anomaly. Imagine the university wants to add a brand new course, maybe advanced quantum physics. But nobody's signed up for it yet. Well, with this table structure, you can't add it, because every single row needs a student ID. You have no way to store information about the course itself until a student actually enrolls. The course exists in the real world, but your database is completely blind to it.
And finally, the deletion anomaly. What happens if the only student in, say, history of pottery decides to drop the class? Well, if you delete that student's record to reflect that, you might accidentally erase the only mention of the course, its name, its ID, everything. The entire course just vanishes from your database simply because one student left. Okay, so these anomalies can obviously wreck a database. So how do we stop them? We need a toolkit. And this toolkit is built on 2 absolutely fundamental ideas: functional dependencies and keys. These are the rules that will let us bring order to all this data chaos. Functional dependency is really the bedrock of this entire process. Think of it as a fundamental rule about your data. When we write X determines Y, it means that for any given value of X, there can only be one possible value of Y. For example, a student ID determines a student name. If I give you student ID 101, the answer must always be John Doe. It can't be Jane Smith tomorrow. It's a non-negotiable rule we have to enforce. So how do we uniquely identify an entire row of data? For that, we use a candidate key. It's a set of columns that can pinpoint one single row and no other. The keyword here is minimal. It's the absolute smallest set of attributes that can do the job. If your key is student ID, course ID, it means you need both of them. Student ID alone isn't enough to be unique, and course ID alone isn't enough either. Now, a really powerful trick for finding these keys is something called calculating an attribute's closure, which we write as X+. Think of it like being a detective. The closure is everything you can figure out if you only know X. You start with your first clue, X, and then you follow the trail of all your functional dependencies. Does X lead you to A? Cool. Add A to your set of known facts. Does A then lead you to B? Great. Add B. You just keep going until the trail runs cold. If your set of facts ends up containing every single attribute in the table, you've found a super key. And if that was the smallest possible set of clues to get there, you've just found yourself a candidate key.
All right, with our toolkit ready to go, it's time to actually start fixing our database. We're going to do this by climbing the normal forms, which is just a series of checks that get progressively stricter to eliminate all that redundancy and those pesky anomalies.
First normal form, or 1N, is the ground floor. It's the bare minimum. And the rule is super simple: 1 value per cell. You can't have a column for phone numbers and then stuff a bunch of them into a single field. Every value has to be atomic, indivisible. Honestly, most modern databases pretty much force you to do this anyway, so our sample table already passes this test. Let's move on up.
Second normal form, or 2NF, tackles a problem called partial dependencies. Now, this issue only ever crops up when you have a key made of more than one column, what we call a composite key. The rule for 2NF is that every other column in the table, a non-prime attribute, has to depend on the entire key, not just one piece of it. If an attribute only depends on part of the key, well, that's a partial dependency, and that's a problem.
So let's apply that to our table. The key that identifies a unique row is the combination of student ID, course ID. But think about it. Student name has nothing to do with the course. It only depends on the student ID. That is a textbook partial dependency. And the fix is to split the table apart. This is called decomposition. We create a new table, student info. Now, student name depends on its one and only key, student ID. Problem solved.
Moving on up to third normal form, or 3NF. This level gets rid of something called transitive dependencies. You can think of this as a second-hand dependency. It's when a non-key attribute depends on another non-key attribute. In our remaining table, our key determines the course ID, and then the course ID determines the instructor name. See that? The instructor name depends on the key, but indirectly, through another column. This kind of roundabout dependency can still cause those anomalies we talked about earlier.
And you guessed it, the solution is decomposition again. We break it apart, we create a course info table, where course ID is the key, and it directly determines all the course details. Our main enrollment table is now beautifully simple. It has one job and one job only, to connect a student to a course. Every single piece of information now lives in exactly one place, determined only by its direct key. This is the heart and soul of normalization.
And finally, we get to BCNF, or Boys Cod Normal Form. It's basically a stricter, more pure version of 3NF. The rule is super elegant and powerful. For any meaningful dependency in your table, the thing on the left side of the arrow must be a super key. That's it. It essentially says there are no side doors or back channels. Every single dependency has to originate from a key. This closes some really subtle loopholes that 3NF might occasionally miss. Okay, so we've been breaking our tables apart this whole time, this process of decomposition. But hang on a second. How do we know we did it correctly? We need to be absolutely sure that we haven't lost any information or accidentally broken any of our rules along the way. First, and this is totally non-negotiable, our decomposition has to be lossless. All that means is that if we were to join our new, smaller tables back together, we would get the exact same data we started with. No extra surprise rows and no missing rows. To guarantee this, the column or columns that link the tables together must be a key in at least one of them. That's the magic that ensures the puzzle pieces fit back together perfectly. Second, we need what's called dependency preservation. This just means that all of our original business rules, our functional dependencies, can still be checked and enforced within our new table structure, right? We can't just throw away the constraints that give our data meaning. We have to make sure they're still protected.
And this brings us to a really important trade-off in database design. Here's the deal. You can always break a table down to 3NF and be 100% guaranteed that your data is lossless and that all your rules are preserved. BCNF, on the other hand, gives you the absolute purest result, zero redundancy. But there's a small catch. Sometimes to achieve that perfection, BCNF might not be able to preserve every single original dependency. So designers often have to make a choice: the practical safety of 3NF or the theoretical perfection of BCNF.
So, after all that climbing through normal forms and carefully splitting up our tables, let's just step back for a second. What was the whole point of this? What have we actually accomplished? Well, normalization is what turns a fragile, brittle database into a robust, reliable one. By systematically getting rid of redundancy, we have completely wiped out those dangerous update, insertion, and deletion anomalies. This is what ensures our data is consistent and trustworthy. It's not just some academic exercise. This is what gives us a flexible design that saves countless hours of painful debugging and data cleanup down the road. We've spent this entire time chasing the ideal of a perfectly organized, normalized database. But here's a final, real-world twist for you. Sometimes, for systems that need insane performance, designers will intentionally break these rules. They'll denormalize their data, accepting a bit of redundancy in exchange for lightning-fast speed. So the ultimate question for any database designer is this: when does theoretical perfection need to step aside for practical performance? Thanks for watching.